So in this video, we're going to look at basically vector valued functions or vector functions. So the main idea behind vector functions is you're quite familiar with the position vector, for instance, r equals 1, 2, 3. Now that's a fixed position vector with coordinates 1, 2, and 3. If you were to draw it in 3 space, with these coordinates, and obviously it would be, for instance, 1 here, 2 here, and 3 here, so somewhere up here. So it would be this vector. Now it's one position, it's a position vector, and of course it's a constant vector. If we introduce the idea that this position vector, or these entities, these numbers here, were not fixed but rather allowed to change, in fact vary, then we get quite close to the idea of what's called a vector function. In fact, a vector function is such that, in fact, it is, we assume that it is a function of t, for instance, with more applications than not, most applications, sorry, t refers also to time, but it doesn't have to. So for instance, now instead look at the contrast between a position vector r and the vector function r of t. You will notice that instead of 3 numbers, now you have 3 functions. But what is interesting is that these are not completely independent functions, in other words, independent of each other. They have a connection, and that connection is the variable, the independent variable t. So this is quite similar to, in fact, the concept of parametrization, which you have seen before. So in other words, the x coordinate here is f of t, the y coordinate is g of t, and the z coordinate is h of t. So with these 3 coordinates and the variation of t, which may belong to some interval I of real numbers, you can get each value of t provides you with the xyz coordinates. So in other words, now instead of this single vector that you see here, a particular value may provide you with this vector, another value of t may provide you with the second vector, a third value may provide you another one, and so on. And for instance, here, or here, or here in this direction. Now, on the other hand, now one thing, sorry, to note is that if you were to connect the tips of all these vectors, you would get a curve, a path. Imagine a particle that was moving from one, sorry, I forgot to connect these here, my apologies. So essentially what I'm saying is that what you would have is, in fact, if imagine a particle, and each position vector represents the position of the particle, and as it moves through space, a new position vector indicates its next position. If you were to connect the path traced out by the position vector, by the object or the particle, you would get, in fact, a curve. And that curve is, in fact, can be called as the path of a particle. It is also referred to as a space curve. Right? So basically what we're dealing with here is a path that is traced out for the vector function f r of t, and we can refer to that as a space curve. So essentially, just like any function, you can draw the function. For instance, a function of single variable x can be drawn in 2 coordinate system, a function x, y, if z can be, we've already looked at that earlier. Here a vector function basically is the path that is traced by a particle as it moves in space. One important thing to keep in mind is a vector function will always trace out a path or a curve. We don't expect to see surfaces and so on here. What we expect to see are curves, in fact. Okay. So let's look at a quick example of what might be expected. So imagine that r of t was, for instance, cos ti plus sine tj plus tk, or simply put the other way, cos t, sine t, and t. You need to be familiar with both of these notations. If you are an engineering student looking at this, the more common usage would be this one. Otherwise, in even most of science and physics, even this notation is actually preferred. However, this is the more convenient notation. But they're interchangeable, and there's no issue in using one or the other. So let's move on. So if we wanted to figure out what was the path traced out by this vector function, this can be very easily done. However, it's a little difficult to try to see this in 3 dimensions, but I'll try to explain how one can work out what's going on. If we, for the moment, ignore the z coordinate, we're talking about cos t sine t. And cos t sine t is essentially, it means that in the xy, if you're looking at this path being traced out, you're looking at a circle in 2D. Or if you were looking at this path of the particle from the top, imagine looking at it from the z-axis, and the z-axis is the axis that's coming out of the screen here, then, and you're looking from the top, what you would see is a circle. But if you looked at it from the side, excuse me, you would see something that is in fact, when you start, for instance, if we were to look at when t is 0, we get 1, right. So if you look at the same thing in the xy coordinate, which looks like a circle, if you look at it in 3 dimensions, the first point here you would see here is when t is 0, we have 1, 0, 0. So that's actually this point here on the graph that you see in the 3D axes. And here, let's say pi over 2, when t is pi over 2, we're looking at y coordinate being 1, and but it's not here on this line. In fact, it's raised up a bit, so it would be, say for instance here, pi over 2, a bit higher than that perhaps. So what's happening is essentially it's circling. So these two are connected by a circle, because in the xy coordinate, in the xy plane, we have a circle. And then what's happening is, as we go further, so this is what's happening. So you get a spiral, which is actually a helix, in fact, the well-known helix. So this is the path that is traced out by this vector function, cos t, sine t, and t. So this is a kind of basically space curve that could be possibly traced out using a vector function. So so here I've actually taken this from the textbook, Thomas's Calculus, 11th edition. So just Pearson's Thomas's Calculus, and here you'll see that there are 3 examples which are very difficult for me to draw, but you will see that essentially. So what you'll see here is, if you look at this curve, look at this sine 3t cos ti plus sine 3t sine tj and a t. So it is increasing value, but look at how it spirals. And if you were to look at this without looking at this expression, it looks like some squiggly lines. Here's another very nice one. This is the cos t sine t j and sine 2tk, right? So it's kind of a periodic, going around kind of an object. And here, look at this. This looks like a spring, one of those springs that kids play with. So this simply demonstrates that how flexible and how amazing it is possible, to get mathematical expressions, in fact, vector functions that can represent such interesting curves. So let's move on.